Good evening to one and all, and welcome to my NPTEL classes. Here is Chemistry Detective to solve your Chemistry Class 11th NCERT Problem 2.19. Let me make you understand this problem. Here it is given that we have an excited hydrogen atom, and in this excited hydrogen atom, electron is present in n is equal to 2. That means hydrogen atom is present in first excited state, because electron in this excited hydrogen atom is present in n is equal to 2 second orbit. Sorry. It is told that energy of electron in hydrogen atom is given by this expression, that energy is function of orbit number of an electron and equals 2.18 into 10 raised to power minus 18 divided by n square in joules. Now we have to calculate how much energy we need to provide in order to remove this electron which is present in first excited state, which is present in n is equal to second orbit. How much energy we have to provide to an electron which is present in first excited state, that is n is equal to 2 of excited hydrogen atom. Not only we have to calculate energy required for this transition, but we have one more thing to calculate, that is what is the longest wavelength of light that can be used to cause this transition. Actually, it is not a transition, it is ionization. Hydrogen atom is in first excited state. Now we have to ionize it. First excited state means electron is present in n is equal to 2 second orbit. Now we have to remove this electron from hydrogen atom which is present in its second orbit. Idea is to solve this problem. Idea is, first we need to have knowledge of energy of electron which is present in its second orbit. Then we need to have knowledge of energy of electron at infinite distance from nucleus, I mean at infinite orbit number. Then third thing, we need to calculate what is the energy difference between energy of electron at infinite orbit and energy of electron at n is equal to 2 second orbit. And this energy difference will be basically the energy required in order to cause this transition, in order to remove an electron which is present in second orbit of excited hydrogen atom. So first we will calculate energy of electron present in second orbit. Then we will calculate energy of electron present in infinite orbit. At infinity, we believe that electron is now not under the influence of nucleus. Atom is ionized. Third, we will calculate the energy difference between energy of electron in infinite orbit and energy of electron in second orbit. Then we will say that this energy difference is basically the ionization energy required to ionize excited hydrogen atom which is in which electron is present in its second excited state. Then we will use Planck's idea that energy is equal to hc by lambda, because minimum energy that is needed to effect this transition is this much. Now longest wavelength that will be required we will calculate by using equation hc by lambda. Let me practice solution of this problem. I will first calculate energy difference between energy of electron present in infinite orbit and energy of electron present in second orbit. And this difference in energy will give me the energy required to excite, to ionize hydrogen atom in its second excited state. I mean, it will give me energy required to take electron from second orbit of hydrogen atom to infinite position, and will be equal to, it will be equal to energy of electron in infinite orbit minus energy of electron in second orbit. Ionization energy that is required to remove an electron from second orbit of excited hydrogen atom will be equal to, now it is given energy of electron in any nth orbit of hydrogen atom is given by this expression, minus 2.18, it is minus here, minus 2.18 into 10 raised power minus 18 divided by n square, that is alpha square, minus 2.18 into 10 raised to power minus 18 divided by n square, which is 2 square. Denominator has infinity is present in denominator, so first term on RHS side will become equal to 0. This term, first term on RHS side will become equal to 0 because in its denominator is infinity and 1 by infinity is equal to 0. Minus minus will become plus. 2.18 into 10 to the power minus 18 divided by 2 2s are 4, and it will come in joules. Delta E, this is the energy required when we are interested to take electron from n is equal to second to n is equal to second orbit to n is equal to infinite orbit, and is equal to 2.18 into 10 to the power minus 18 divided by 4. This equation will give me the energy required, and delta E comes equal to 2.18 divided by 4. It comes equal to 5.45 multiplied by 10 raised to power minus 18. It comes equal to 0.0.5 0.545 into 10 to the power minus 18. And if I will bring this in scientific notation, it will come delta E is equal to 5.4 into 10 to the power minus 19 joules. This much energy we have to provide to electron present in second orbit of hydrogen atom in order to remove it completely from hydrogen atom. Now we have to calculate wavelength, and before calculation of wavelength, I can give you general formula for ionization energy required in order to take electron from nth orbit to infinite. This is the energy required, energy that we have to provide in order to take an electron from nth orbit of hydrogen atom to infinite orbit. I mean, this is the energy required to ionize hydrogen atom in which electron is present in nth orbit. This is the energy required to remove an electron from hydrogen atom in which its electron is present in nth orbit, and it is equal to ionization energy required to remove an electron from first orbit to infinite orbit divided by n square. Energy required to take electron from first orbit to infinite orbit divided by orbit, square of orbit number in which electron is present, and energy required to remove electron from first orbit of hydrogen atom is 2.18 into 10 to the power minus 18 joules divided by, in electron volts it is 3.16, but in joules it is 2.18 into 10 to the power minus 18 divided by n square. This is the general expression. Suppose in any other question we are asked to find the energy required to remove electron which is present in third orbit of hydrogen atom, then we have to divide that time 2.18 into 10 to the power minus 18 joules by 3 square. Suppose it is asked to find energy required to remove an electron from fourth orbit of hydrogen atom, that time we have to divide 2.18 into 10 to the power minus 18 divided by 4 square. And what is this 2.18 into 10 to the power minus 18 joules? It is the energy required to take electron from first orbit of hydrogen atom to infinite orbit, because it will come equal to 2.18 into 10 to the power minus 18 divided by 1 square, and 1 square means 1, so 2.18 into 10 to the power minus 18 divided by n square. This is general formula. Now we have to calculate wavelength. We know delta E is equal to hc by lambda. Lambda will be equal to hc divided by delta E. Now lambda we have to calculate. Lambda will be equal to 6.626 into 10 to the power minus 34 into 3.3 into 10 to the power 8 velocity of light in vacuum. This is Planck's constant. This is velocity of light in vacuum divided by energy required, which is 5.4 into 10 to the power minus 19, and wavelength required will come equal to 3.647 into 10 to the power minus 7 meter. This is the wavelength required. This is the longest wavelength required. This is the longest wavelength which radiation need to have possess in order to effect a transition in hydrogen atom, during which electron has to go to infinite distance from second orbit of hydrogen atom. And in angstroms we can report it lambda is equal to 3647. It will come 10 raised to power minus 3, 10 raised to power minus 3, 10 raised to power minus 7, 10 raised to power minus 10, and 10 raised to power minus 10 meter is 1 angstrom. In angstroms it is equal to 3647, and in meters it is 3.647 into 10 raised to power 7 meters. Class 11 students, be blessed. Take good care of yourself. This is what I have got for you today. See you day after tomorrow, as tomorrow is turn of class 12 students. Allah Hafiz.